So this set of slides is the last set of slides that will cover kind of general streams before we get into the parallel streams topic. And what I want to do here is I want to compare and contrast Java 8 streams with other technologies, other designs that you may be familiar with or you should know about, so that you'll understand how this compares and contrasts with other things that you may have heard of. So we'll also talk about how Java 8 streams compare and contrast with other Java libraries, like collections and I/O and so on. So a Java 8 stream is basically an implementation of a famous pattern called the pipes and filters pattern. And you can read the original description in the POSA 1 book, which is shown here. And you can also read a revised discussion about the pipes and filters pattern here in this paper at the URL at the bottom. And what the pipes and filters pattern does, what its intent, is to divide the tasks in an application into multiple self-contained data processing steps. And then you connect these steps together by intermediate data buffers to form a data processing pipeline. So you would have some input from some place, like a source or a device, and you have the input come into a filter, and it does something to the input, and it transforms it, and then it generates the transformed data, and it's buffered, and then you have a pipe, so it's buffered into the pipe. Then the next filter takes the data from that pipe, does something to it, puts the output into a buffer, which is part of a pipe. Then the next filter processes it, and so on until it's finally finished. So that's what people think about as a pipeline, right? You pipe the data through a set of filters or transforms. Don't read the word filter here to mean filter in the context of Java 8 streams filters. Think about them as transforms. They do something to the data. There's a bunch of known uses of the pipes and filters pattern, right? So this is one that I actually have in our house. So the water comes in from the outside, and then it goes through a bunch of filters to do various things to improve the water quality. So that's pipes and filters, right? I mean, literally, you've got the pipes that are taking the water, and you've got the filters that are removing various impurities. Who knows if this actually makes a difference? My wife feels happy about this. I can't really tell the difference, but it's cheaper, or not cheaper, it's more ecologically sensitive than buying bottled water, right? So you get your pipes and filters pattern applied. Another example, maybe a little bit more close to home, unless you have water filters, is the UNIX command line shell pipeline. So if you're familiar with Unix, then you can do stuff like this. You could go ahead and look at all the files in the user bin directory. You can pipe it, that's what the vertical bar stands for. You could pipe it through a filter program called SED, which stands for Stream Editor, that strips out the directory portion. We could then get stuff that matched a certain, you could match something using a matching. You could look for something that began with Z. Then the output of that would be fed through the sort command, and then you could go through and remove all of the new lines and print the result in a single line. Right? So that's a good example of a pipeline command, command line instruction you could give in Unix, in the Unix shell, that would be the pipes and filters pattern. And so that's basically the idea. You pipe it through a bunch of stuff, and this is just showing sort of how it works. You get standard in from the keyboard, and it goes through a set of programs, or what they call filters in the pipes and filters pattern, and the standard output of one program goes into the standard input of the next program. So it's a pipeline of stuff. Very famous. People don't do as much of this anymore because more and more people are using graphical interfaces. But if you're an old school Unix shell programmer, you'll be very familiar writing this kind of code. There's something else called System V Streams, which is a framework for implementing layered protocol stacks in modern operating system kernels. This was developed a long, long time ago by Dennis Ritchie, who also invented Unix, and it's basically the same kind of idea. You have data flowing in from a device through a set of modules that transform the data, so it's delivered to the user, And then likewise, if the user generates data, it flows through a bunch of modules on the outgoing path to reach the device driver to be sent across the network or stored in a file or whatever. So these are all examples of the pipes and filters pattern, and Java streams are just this pattern implemented in Java with Java syntax and Java semantics and so on. There are also other features in the Java class library that have the word streams or stream. And this is very confusing to people when they're first exposed to this, because they think, oh, I know what a stream is. A stream is a way of dealing with I/O from a file or from a terminal or whatever. And that's very confusing at first glance. The thing to remember is that Java I/O streams are different from Java streams. So Java I/O streams are used to take data from a source and stream it to a program. And then you can also take a program and stream it to data sync. So that's what I/O streams are. And that's not at all what we're doing here. Although you could have I/O involved in a Java 8 stream, but it's not the same concept. Of course, they're often used together, right? So people will often take data that comes in stream format as the input to a Java 8 stream. So that's even more confusing, because now you have two different types of streams that are worked together in various ways. In fact, if you think about some of the examples we gave last time when we were talking about buffered, when we were talking about the factory methods for streams, I gave a couple of examples where we had buffered readers, and we had the files class and so on, and they were Java I/O streams classes that had methods added to them in Java 8 and beyond to create Java 8 streams from input sources that were Java I/O streams. So that's even more sort of mixing. It's almost like a homonym. You're using the same word, but they mean different things. Java collections are also different from Java 8 streams, although they often get used together in many different interesting ways. So a collection is an in-memory data structure that can store, retrieve, and manipulate groups of elements. So a classic example would be something like the Java array list, where you've got a bunch of elements in the array. In this case, we've got 5 elements, and each of those things is, basically a reference to some object that has some values. In some ways, here's an analogy just to think about. It's not a perfect analogy, but it'll help make it more clear. A collection is kind of like a DVD, right? In the sense that everything is stored statically in the DVD. Now, the difference is in a collection, you can read and write to it, whereas in many DVDs you can't. But let's assume we have a writable DVD, or writable CD. The basic idea is that it's all there. You can plug it into your DVD player if you ever still have one of these things, and you can play whatever you want to watch, and it's all there, just like a collection has all the data in it. In contrast, a stream is a data structure that processes elements on demand. And so you can manipulate the elements from a collection without explicitly iterating over them. That's the whole implicit iterator stuff that we just talked about a second ago. So from this point of view, a stream is more analogous to a flow of bytes in a streaming video, right? So unlike the DVD analogy that we talked about a second ago, where you have everything stored on the disk, the DVD, and it's all there, which is kind of like a collection. With a stream, it's more like a flow. And as we've talked about in the past, at least in theory, it's an infinite flow, right? So it could go on forever. Practically speaking, you don't go on forever because you'll burn up your computer cycles and something else. But in theory, you could have a stream of things flowing, a stream of elements flowing through a stream. So in that case, the content can be dynamically received and processed. Although, as you see with a Java stream, Java 8 stream, the number of things you can do to it are fixed. So you have a fixed number of things you can do to it, but you have sort of an infinite flow of stuff that can go and process stuff in that stream. Yes? Well, it depends. So an I/O stream usually is connected to something that will be sort of fixed, right, like a file. But in theory, you could have I/O streams that would be flows of bytes. The main idea is it's just a stream of data, and any structure that's in the data. The use of the word stream in the context of IOStream is that it's up to you to figure out what the stream's format is. It's just giving you a bunch of bytes. That's what it means in that context. So they have some similar relationships, but they're fundamentally different concepts. Now, the thing to remember here is that there's factory methods that can be used to convert collections to streams and vice versa. So we can take a collection, especially all the built-in collections, and we can say, hey, make a sequential stream from the collection, or make a parallel stream from the collection. And that's how you can go from one of these things to one of the things on the right. And then likewise, after you've done all your processing and transformation in a functional way through a bunch of composition of functions using the Java 8 stream, then when you are so inclined, you can convert the stream back into some kind of collection using collect as one example. OK, so those are just a few things. A lot of times people get a little bit confused with some of these concepts, and I wanted to clarify them. Here's a very simple example of manipulating a Java collection. We've seen something like this before. So we've got ourselves a bunch of URLs. And we turn them into a list. And then we go ahead and, in this case, we iterate through the list, not using a stream, in order to be able to basically replace stuff and update the set of URLs. And I think you'll agree with me that this code is a little bit complicated to program. In contrast, here's the same thing, except now we're going to use a stream. So we have our arrays, just like we did before, except this time we're going to go ahead and convert the array into a stream of strings. We're going to do a transformation, replacing the substring with another string. And then we're going to go ahead and create a collection result using our collector, converting it into a list, and storing it into this list of strings. This is actually not doing the URL transformation, but it's just converting from one form to another. Like iterators, elements in a stream can only be visited once during the stream's lifetime. This is really important to remember. Once a stream is finished running, once collect is run and you're done, you can't take the same stream and do stuff to it again. You have to start by giving it a new data source, or the same data source, just doing it over again. So you can't use a stream more than one time. That's often very confusing at first. I remember when I was first learning about streams, I was somewhat flummoxed because I wrote this program and it didn't work right, and I realized I was trying to reuse a stream more than once. Yes?
Somewhat. When I was looking.
Yeah. Oh, yeah, yeah. Uh-huh.
Does that mean each thing is pulled through all of this?
Great question. So the question basically is, how do these things work? Do we go ahead and generate a stream of strings from this array of strings, and then we call map on, we call the lambda expression for each of those things, convert them all. Then we take everything that's converted and we collect them all. Does it kind of go left to right entirely? It's like a typewriter. You type and type and type, and then you hit control. You hit the line feed thing, and it goes back to the beginning and does the next row. That's not the way it works. I'm going to focus on sequential streams here. Parallel streams is the same thing. It's just more interesting. But for sequential streams, what actually happens is when collect gets hit, it goes up to the source and it says, give me your first item, please. And then it takes that first item and it runs it through all the intermediate operations, does whatever transformations and filtering and whatever is required, and then it gets the result. And after it takes that result and accumulates it, as is the case here, it then goes and it says, let's get the next item. And we'll run it through every element. So it's essentially doing it item by item, pulling the items through the list of transformations or filters. Yeah?
Just to follow up on that, then if it's filtering, let's say it fails.
Yes. So if there's a filter operation and it decides for whatever reason it doesn't pass the filter, it's thrown away, then it'll start again and pull the next item. Exactly. So if you were to compare the performance of a stream in terms of the number of steps performed versus a loop that did the same thing, they would have exactly the same number of steps. And this is important, especially when it gets to short-circuiting operations. So we haven't talked a lot about those, but we'll talk about them more later. So short-circuit operations would be things like limit where you're going to say, I only want to process the first 100 elements in this stream. And after the 100th element is reached, you stop. So it doesn't process all the elements over and over again and then finally, sort of accumulate them all like, oh, now we've got 100 of these things. So it'll only do the first 100 steps. So the streams are carefully designed to only do the minimum amount of processing necessary to get the job done. Now this gets a little bit more interesting in parallel streams. We'll talk about that later. But for right now, imagine for sequential streams, it's really the same amount of effort as writing a loop. Just cleaner because we have internal iteration, not external iteration. Yeah. What if you didn't have the collect? Great question. So if we don't have collect, then the terminal operation will never be reached, assuming we don't have reduce or for each, right? There's other terminal operations. But if we don't have a terminal operation like collect, then the stream will never run. And that's because streams are fundamentally lazy. And the image that should show up is my sleeping cat, right? So the streams are lazy. They don't do any work. And they only do work when a terminal operation is hit. And we'll talk about how streams are actually implemented later in the parallel stream section. But basically what happens is when your code runs, when this code is executed by the virtual machine or the execution environment for whatever's doing your Java code, what it does is when it sees this stream, it actually builds up a linked list of these operations, these intermediate operations. And it builds it up an internal data structure that's a linked list of these things. And then when the terminal operation is hit, it starts to pull the data through the linked list of intermediate operations that do the transformations and the filtering and so on. And so if collect is never hit, then you just have built a stream that will do nothing whatsoever except consume memory and confuse you mightily because you'll have no idea why the stream doesn't do anything. Now, having said that, there just has to be a terminal operation running somewhere. So it's perfectly plausible to build up a stream, and then you can even have a function that returns a stream as the return value, and that's fine. It's just that somewhere that return stream needs to have a terminal operation to trigger it to begin to run. And we'll go through this in a little bit more detail when we talk about the internals of streams, which comes up in the parallel streams section. The key to, this is probably just overkill at this point, but the key to the power of Java 8 streams is their ability to chain together transformations. So you'll notice here that this is where we were making ourselves a list of strings, right? That was the stream. And if we wanted to make this a list of URLs as opposed to a list of strings, that's all we have to do, right? We just throw in another transform. We take the stream of strings that comes out of the first map, and then we go ahead and add a new conversion that creates a URL from a string, and then we collect that. So now we have a list of URLs as opposed to a list of strings. And this ability to just trivially change the semantics by adding a new pipeline stage is really at the heart of this. And that's, by the way, that's exactly conceptually like a UNIX pipeline where you can just add new filters in between the vertical bars in order to transform the flow of data through the stream or through the pipeline. Yes? Sure. Yes. Yeah, so the question is, can you have intermediate steps that would, the way you would do that, by the way, is, let's pretend like we left the collect off here, right? So you would say something like stream of URLs equal stream.of.map.map. You could write that code and you could put that in another method that was called return URL stream or something like that, or make URL stream or something. And that would just do that piece, and then you would have to call that function somewhere and then have a terminal operation that would cause it to start to run. But it's absolutely fine and very common, in fact, to have methods that return streams. That's perfectly acceptable. And I'll show you some examples of that later when we talk about more interesting uses of streams. Yeah, that's a great question. And you can see here again, that this is showing how we can put things together just by adding a new stage in our pipeline. And then I'm also showing how the rethrow function can be used to convert checked exceptions into a runtime exception. OK, so that's the end of the comparing and contrasting Java 8 streams with other things in Java, right? Like I/O streams and collections and other stuff that you'd find in the Java class library.